Right, so as I said, your final exam for your statistics is cumulative. It covers everything. And where originally I said most of it was going to be the last bit of material we covered, as I was writing the exam, it started getting really bulky. I went through it as well just to make sure that the timing was well on it. So I've actually cut it down to, let me see, I think about 19 problems. And just because some of you are in the other section, if you were in this section, the other section, you have slightly different exams because there's a slight difference in material we covered, but it's got the same point out and the same number of questions. All right. So kind of just do a quick run through of some of the material on the older stuff, and then I'll spend a little bit more time on the last stuff that we have a little more struggle with. Ooh. What this thing is doing. There we go. There's a little too much on my screen. So when we started out this class, we did a bunch of definitions. So I will tell you right now, I did not put anything about descriptive or inferential statistics, and I did not put anything about a statistics or a parameter on there. So those two I've gotten rid of. Just because those are a little confusing questions. There was, and as I say, your homework system does not help with trying to answer those. Like I said, 1 and 2, I wouldn't really worry too much about. Something like 3, because we do use that as same information later, maybe not just blatantly like as one problem we would use. So 3, so we had a little bit of struggle sometimes still identifying a sample in a population. So anytime we mentioned a sample, this was just part of the group. Or a part of the whole, and your population was the whole. So population is always everybody. So political scientists surveyed 32 of the current 115 representatives in state legislature. Your population would be the 115 because that represents everybody in the state legislature. And the 32 would be your sample because that's the only part of it that we took. So there is a question like 4, because once again, it was very important that we know what kind of statistic, what kind of data that we had here. So once again, I kind of cut this down to like 4 of these. You don't have to do every single one of these, but determine if each observation is qualitative or quantitative. So duck feathers are soft. Would that be quantitative or qualitative? If you're not sure, remember qualitative. This was usually not numbers. But something that we could talk about is like categories. So it was usually things that were like descriptors. And then quantitative was actually dealing with quantities. And this was usually numerical. So that being said, you could have numbers and qualitative data. It's just those numbers are not meaning a measurement. What you have numbers is just that they're going to define a category. So an example we have is like tornadoes. We have like an F0 and an F1 and an F2. That was not like a number that was a quantity or a measurement necessarily. It was a categorization for that tornado. So there's characteristics that made us characterize it that way. So in this case, our duck feather soft would have to be qualitative. Real Salt Lake beats, sorry, that's a weird way of saying it. We'll go Salt Lake beats the Colorado Rockies 3-1. And then we're talking about a score there. So you're talking about quantities or measurements. So that'd be quantitative. This one I hated. Technically, You have more boys than girls, that comes out as quantitative. I didn't ask you one like that one, that just appears in here because it's talking about quantities again, about amounts. The path of the delicate arch is 1.7 miles. That also be quantitative. And he dyes her hair yellow and they put in the wrong dye. That one is qualitative. She's not killing her hair, she's dyeing it. So I did this a little easy, things like number of things that you had, or titles or things like that, something that's a little more obvious. Like I said, I did not ask one like C. You might have something like duck feathers are soft or something like that, but so showing the difference between qualitative and quantitative. And this actually expanded a little bit because we had qualitative, then we had discrete and continuous. And these were both quantitative data types. So what I ask you is if data is qualitative, and then is it quantitative and discrete, or quantitative and continuous? And we said kind of the go-to, so discrete was things that are usually like whole numbers. So discrete usually consisted of things that we're talking about amounts, like the number of dogs I have, or the number of dollars I make, things like that. That's a discrete amount. Like money, we always talk about discrete because at the least it goes down to cents. Continuous means it had like the spectrum of values that between any two numbers, there was an infinite amount of values are in there. And continuous usually referred to things that were measurements. So like temperatures worked under this because temperatures, between 98.2 and 98.3, there's also a variety of different temperatures in there, or heights and things like that. So going back up here, we're going to do this one and then I'm going to go up. In a study of data, you collect a number of shirts of each marathon runner. We're talking about a number of shirts. So we have a number, so we know it's going to not be qualitative. And since it's amounts, it would end up being discrete. So I just wanted to point out, if you're doing these ones here, Rocky Mountains, that would be discrete because we count scores as whole numbers. But the delicate path, because that's a measurement in miles, that would be continuous. Number 6, the house, the house is of a color, would be qualitative because it's not doing with numbers. Get to move the right one, is a little bit of pain here. What's this thing doing? I'm trying to move a little bit. There, no. Okay, we're close enough, I guess. This is as close as we're gonna get. The data you collect in a study, the data you collected is years of cicada emergence. Once again, that one would be discrete because we're talking about it in years. If I talked about it in like minutes or something like that, it'd be a little different. Okay, I'm going to kind of skip these two and go to 10 here. I also ask you about sampling methods. So we had simple. So simple was like, sound like it was just really simple. We didn't do anything special. Systematic, this was like when you took every nth item. Cluster was when we talked about geographical clusters. So this is where we talked like we'd only go to certain counties or to certain blocks or certain streets. So it was geographical. Stratified was groups based on a descriptor of some sort. So this would have been like gender or age. So in this case, we're making groups based on, like I said, gender, age, medical issues. Income, things like that. So something that separated group based on something like that. And then convenience was basically doing this the easiest way we could. So I took one of these out of here. I didn't do simply random because it's kind of confusing with convenience. So here, every 15th phone call, a number, call every 15th phone number on every 5th page of a phone book. That would be systematic. So that'd be your B. I'm going to write it right here next to it. Call all students in your class. That would be convenient because they just happen to be there in your class. You don't have to seek them out. Basically, it sounds like the worst way to sample. It's probably convenience. If you pull 50 names from a hat, this was the one that was actually like simply random. Because I had to put a little bit more work into it. I was trying to randomize it as much as I can. Randomly select 2 tables in a cafeteria and survey all the people. That one is geographical because we're picking groups based on location. Not geographical, sorry. That's clustered. Dividing the population by age and then selecting 5 people from each group. That would be your stratified. Sampling method. All right. Then I asked some questions that had to deal with histograms. Sorry, this thing about replacement shouldn't have been in here. This was a leftover question that I thought I took out. So we're not going to do one like 11. We're not going to do one like 8 either. We may do one like 9. So the bar graph below shows the percentage of students who received each letter grade on their English paper. The class contained 20 students. What number of students earned a B on their paper? Showing percentages. So this is 50%. So it's wanting you to say you have 20 students, you took 50% of them. It would be 10 of your students got a B. So like I said, there's just a few of them. I'm just reading some histograms. Yeah, I took out 12 too, so you're not asked about levels of measurement. So this one here is we have groups of adults. We're asked how many children they have, and we see the data below. So this is actually telling me not percent number of kids. Or number of people who have that many kids. This is just a frequency. So if we were asked how many adults were questioned, that means I have to figure out each time somebody answered, that was an adult they talked to. So 4 adults said they had 0 kids. We have 6 adults said they had 1 kid. 2 adults said they had 2 kids. 1 adult said they had 3. 1 adult said they had 4, and 2 adults said they had 5. So I have 4, 10, 12, 13, 14, 15, 16. 16 adults were questioned. And then what percentage of them had 0 kids? Well, it would have been 4 out of the 16, which is 1/4 or 25%. I got a question. I didn't ask you to do this again because this was just time consuming and you all did it correctly the first time. So no question like 14. And no question like 15. I wasn't going to ask you to do those frequency distributions again. 16, like I said, that's going along with looking at histograms. That is another kind of question you might get. So class width. So this is limit grouping that you see here. The limit grouping was that I'm basically saying that here I'm looking at people between, or data, I don't know what my data is about, but I'm looking at values between 1 and 6. 7 is just telling you where the next class starts. So each one of these is telling you where the next class starts. So in this case, if you're asked where the class starts, when you're asked class width, you're just asking about the difference between those classes. So class width was always the difference between 2 consecutive and what we call these is class boundaries. So it's 2 consecutive class boundaries. So in this case, it doesn't matter which 2 I pick as long as they're consecutive. I could pick 7 and 13, and I just look at the difference between them. And the difference is 6. I could just look at the difference of these 2 numbers. Just as long as they're consecutive, it's telling me that each class has 6 numbers in it. This class has numbers 1, 2, 3, 4, 5, and 6 in here, where this one has 7, 8, 9, 10, 11, and 12 in it. So like that. This is telling you there's 6 numbers in that class. What is the sample size? We already asked this. But we did ask questions like this. How many people answered 25 or more? So when you're asked something like that, we know that this is where 25 starts, and then this is more. So we have 3 people here, we have 8 people here. So 11 people would have answered that. Wait, yes, 11. Thought I miscounted for a second. Once again, I didn't necessarily ask about quartiles. I do ask about interquartile range, because this part most people were okay with. This one we had issues with. So your interquartile range is the difference in your Q3 and your Q1. And if you remember, when we have a 5-number summary, what this 5-number summary is it's giving me my minimum, then my first quartile, my second quartile, which is my median, my third quartile, and then this is the maximum value. We only really need to do this just the quartile 1 and 3. So if we do the difference between those, that's going to be Q3 is 16, Q1 is 4, so the difference is 12. An observation is considered an outlier if it is below, and what we said before was it's this first quartile minus 1.5 times the interquartile range. So it would be 4 minus 1.5 times 12. I thought I had a question there again. So 1.5 times 12 is going to give me an 18. So it's going to be minus 18, which is going to leave me a minus 16. So if I had any data in my set that's less than negative 16, that's when we consider it an outlier. Or if it's above, Q3 plus 1.5 times the interquartile range. So my Q3 was the 16, so we have 16, but this time we're adding on that 1.5 times 12. So it's going to be the 16 plus the 18. Where? So in that case, it'd be 34. Like I said, I just sort of picked and choose some of these questions that were some of the earlier stuff. So I'm not asking you everything. It was mostly the things that you guys kind of struggled on the first time, so giving you a chance at it again. Do we have to do? No, you do not have to do number 17. Like I said, I was trying to hit things where I cover a little bit of everything without taking up too much time. So 17 is out. I believe I removed percentiles. So let me just check here really quick one more time. Like I said, I couldn't quite hit everything. Yeah, so percentile I did take out. And a question with a box plot like this. So as far as mean, medians, and mode go, I didn't make you calculate those because we have a calculator that will do that for us. We know how to do it. What I asked you is more like a question like this. So I identify which would be the better measure of center of the data below. So if we had a symmetric bell curve, which is what we usually identified as being a normal curve. So that's our normal distribution curve. We like to use a mean because if we're a symmetric bell curve or basically a normal distribution, if I have mean, I can do standard deviations and all this other fun stuff that we get to do. So if it's not normal, something, so if this would be skewed, maybe bimodal, bimodal, what was the other one we had? Multimodal. Anything like that, then we would end up using a median. So either you're going to have one that's going to be finding the mean. Basically, your choices really boil down to, is it mean or median? So you get giving all this extra stuff in here. But like I said, it pretty much boils down to this. Is it a mean or a median? This data is definitely skewed, so we'd use a median. Like I said, if it looked nice like this, then I would use a mean. So any kind of distributions like that were the ones that we said were not normal. Okay, box plots and percentiles are not going to be included. I'm not going to make you do those again. And then what was it? Mean, median, mode. I'm not going to make you calculate it. You just have to look at data and tell me if you use the mean or the median. Hopefully you're able to hear me that time. This is just a pictures of kind of distributions that are not normal. This one we almost never seen, but there's one that makes a triangle. That's also not normal because it's not a bell shape. Okay. So I didn't ask you ones like this, so you don't have to identify necessarily outright. You just have to identify enough basically to tell me if I'm using a mean or a median. You don't have to tell me if it's uniform, bell shaped, how it's skewed, or anything like that. I took those out as well. All right, standard deviation. I'm not going to make you calculate it. What I'm going to do is ask more questions that are along the line of 28. So like I said, I was trying to like get some things without overwhelming us on calculations here too much. So most of your calculations you're going to have are going to deal with z-scores, probabilities. There's like one, I think, yeah, z-scores, probabilities. That was the other one. What am I thinking of? Hypothesis testing and confidence intervals. So as a reminder how this works, the height of adults who identify as American have a mean of 69.5 inches and a standard deviation of 2.63. Adults who identify as women in America have so this is men, this is women. Women have a average of 64.6 and a standard deviation of 2.56. So a self-identified man is 6'3". What is his z-score? So in this case, we're talking about an individual. Or in this case, like I said, an individual X, we're not talking about groups. So when we do that z-score, it's going to be the X minus mu divided by sigma. So 6'3". Second, 6 times 5, 26. I think that's 71. I'm just checking here again. 75. This is 75 inches. So X is going to be my 75 inches. We said that the average for a man was 69.5 with a standard deviation of 2.63. Yeah, you gotta be careful when you do these, because I accidentally moved my calc in the wrong place. But like I said, if you do this with like parentheses over the top here, you're less likely to make a mistake, but we get in with a 0.29. The z-scores are almost always rounded to 2 places. I have one that rounded to 1 place to make the calculation easier. Once again, if it's the woman, 5 feet 6 inches. So that one is 71 inches tall. So that'd be 71. But this time we're just taking away using all the measurements for a woman. I didn't ask you the relatively taller thing again, but I'll go through it here quickly. This we get 2.5. So relatively taller is the woman because relative to other women, she is taller. Like I said, there was a few people who tripped on that as a question, so I just want to go through that again. Okay. So you'll have to do z-scores of some type. Probabilities. I will make this very easy for us. I asked us, where is it here? Second, I'm trying to find that one I asked you. Random disjoint. I think I missed it. Yeah, okay. So it's more like the one you'd have here with 33. Except I made it really easy so you don't have to look at this whole graph here. But it says, if you are selecting cards at random, what is the probability of selecting a 10 or a club? just as a reminder here, that tens and clubs, they overlap, or what we says are not disjoint. So we need the probability of a 10 plus the probability of a, oh, probability and club are disjoint. So this is just probability of a club. A second, where was I? They're not disjoint, so you need a 10 and a club. There you go. And then you have to remove the probability of a 10 and club at the same time, because they're not disjoint. So we know we have 52 cards. 4 of them are a 10. We have 13 out of 52 cards are a club. And there's at least one card that is shared by the tens and the clubs. So we have to remove that one time. Say 26, I'm at 16. I saw a mystical 10 in there that was not there. And as a reminder, when I give you anything that comes out as a fraction, if I can, I reduce that fraction. So you have basically one probability question where you're dealing with those kind of probabilities. Like I said, I really cut down on the probabilities a lot. Okay. So you have another question. There is combination. So I didn't worry about 39. This is like a question of between like 38 and 40. So you have a question, it's a combination of those two. So you're asked to fill out a chart, but then you are also going to give me an actual weighted mean or expected value. So a company estimates that 0.5% of their products will fail after the warranty period, but within 2 years of purchase with a replacement cost of $450. So you always are going to have a chart like this. You have two choices. Either it's going to fail or not fail. And essentially what you're interested is the profit that you're making. So you are the company. So you want to know what your profit is, and you want to know the probability of that profit. So we know that if this thing doesn't fail, then what we're going to do is we're just going to make the warranty price. So if they offer a 2-year warranty at 70%, we want to know what is the expected value of each warranty. So if the thing doesn't fail, we just make off with $70 right off. That's what we get. And as a reminder, when you talk about this percent, this is 0.5%. We're going to write that probability as a decimal. So what we have here is this is the probability of failing. So the probability of not failing is just whatever's left over. So it would be 0.995. Then the probability, the money that you make if this thing failed would be you get $70, but if it fails, you have to pay out that $450. So this is a negative $380. So when you do your weighted or expected average, or expected value, sorry, there's just so many ways we call this expected value. That was really is going to be the profit. So if this thing fails, we pay out $380, but the probability that's going to happen is 0.005. And then we're going to add to that, we could just earn $70 because it doesn't fail at all and they pay the warranty. And the probability of that is 0.995. Like I said, I kind of combined 38 and 40 for this question here. So instead of asking you two different questions, just turn it into one. A lot of these were kind of like, if there was one thing I wanted you to walk away with knowing, these are the kind of questions they would be. But my expected value of the warranties is, each warranty is expected to actually bring me in about $67.75 or $67.75. Yeah. If I have another question, nope. All right, so as far as the standard normal curve goes, remember the standard normal curve takes everything and writes it as z-scores. So the mean always is going to be 0 because that's the z-score of the mean. The standard deviation is always going to be 1. All right, so we had questions like this. I'm probably not going to do every single one of these. I'm going to kind of hit some. And I didn't actually give you the chart for this. I kind of just gave you the mean and the standard deviation. But if we look at this data, I think I need to scroll up just a little bit. There we go. We have the price for a certain model of an HD TV. The mean price is going to be $2,000 with a standard deviation of $100. That means 68% of the TVs, what they're going to be between is 200 minus 100, because that's one standard deviation, to 2,000 plus 100. So this is what we called your empirical rule. So I have a question that I just asked empirical rule. I'm not trying to confuse you with anything else. You're just doing empirical rule. So what we get is 68% of my TVs are going to be between 1,900 to 2,100. Then we know that 95% of TVs, this time, this is 2 standard deviations away. So we take away the standard deviation twice, and then we add it twice to the other side. So this is just saying there were 2 standard deviations out, but this is a range of $1,800 to $2,200. So I got here, this is where 95% of my data is. And then the last one was 99.7%. So this is the 2,000, but this time we take away 3 standard deviations. And then for the other side of my range, I add 3 standard deviations. So in this case, this is going to be, $17,000 to $23,000. So we expect that that 99.7% of this particular model of HD televisions, if we want to try to go buy it, is going to have a range between $17,000, sorry, let's try it again, $1,700 to $2,300. We expect 95% of this particular TV to be priced between 1,800 and 2,200, and we expect 68% of them to be priced somewhere between 1,900 and 2,100. So you're not asked like the less than questions, you're asked more of these in between ones. So approximate, oh, not that one. It's like I'm trying to find the one I need here. So let me erase these and put in the questions that I actually asked because I tried to make this easier and quicker. And these are kind of questions that we were asked before. So it'd be questions like, how many TVs are between 1,800 and 2,200? Like I said, if you make this little chart here, it will go quick. So how many are in this range? Well, we know that's going to be 95%. 99.7% of TVs are in what range? The range of values that you would need to look at would be, in this case, we see that it's going to be between the 17,000, sorry, 1,700 to the 2,300. So those are kind of questions I try to simplify it down to instead of asking you a bunch of probabilities. I'll just basically just quickly going, can you do the empirical rule? Question here, what was it? Yeah, so I ask you the percentage between two values. And then I ask you for a range if I like said, you know, like where's 68% of them or 95% of them or 99.7%. So you might have to give me that range. Like I said, just a real simplified version of this. So a lot of these were actually taken from your previous test and reworded. So you expect to see things that look very much like what you had in exam 1 and 2. Okay, so we already did one where we found a z-score, so I'm not going to do a z-score again. I'm going to do one more like this one here. So I kind of split some of this up a little bit about how I'm asking you it. So don't expect your questions to look exactly like these. So I'm actually going to do this one here because this will be easier one to start with. So this is the patient's recovering time from a surgery. So a patient recovering time for a particular surgery is normally distributed with a mean of 63 days and a standard deviation of 2 days. And we want to find what is the probability of spending 8 days or less in recovery. So it's just asking you for nothing about a mean here. We're just dealing with X's. So every time we want to find these probabilities, we have to find z-scores. And we're finding them for individuals. So if you look at this data, it told us right here that the mean days for recovery is 6.3 days with a standard deviation of 2 days of recovery. So the z-score for 8 days would be 8 minus 6.3 divided by 2. The way I ask this question is instead of breaking up and having one question about z-scores and then one about probabilities, I ask you for the z-score and the probability just one time. So we get a z-score of 0.85. So all those calculators we had that were z-score calculators and everything, I've actually linked those for us in the exam. Still sharing, right? Yes. So we said that the z-score is 0.85. And we wanted the probability of less than. So remember this first one, it's got a less than sign, that is less than. So how many people recovered in less than 8 days is going to be the 0.80. What did I say? Round to the nearest 10th of a percent? Oh, so percents. So we'd write this as 80 point, let me go back again, 0.2. So the next one is asking us about 6 days in recovery. So we were looking at 6 days. What was the probability of taking more than 6 days to recover? That is a z-score of negative 0.15. We go to your z-score. And this time we're looking for greater than, so more than 6 days. So we have to use the greater than, and that is going to be 55. So it will be actually 56%. And then when you're asked in between, that means you need these two z-scores. So for between 6 days to 8 days, 6 days was negative 0.15. 8 days was 0.85. Those were my z-scores. Oops. So we're looking at this one that binds them in between. So we put in the smallest z-score. Oops, that wasn't a point. And then we put in my largest z-score. And we get a probability here, and this one's going to be 36.2. Keep hitting the wrong one. Okay. So just kind of go through this part here quickly. So if you're asked a question like this one where you have a percent and you're going backwards, like I said, I don't ask you necessarily with this kind of question, but I'm going to ask you something similar. So this one is, this company makes widgets, and these widgets have a mean of 42 ounces with a standard deviation of 9 ounces. And I'm actually going to ignore this first part, because what I would ask you is, I'm not going to ask you empirical rule more than once, would be a question that is going to be more of the lines. So instead of asking like this question here, I would actually reword this to using z-scores. .7% of widgets lie between . So just as a reminder, if you are given a percent, and we use the z-score calculator, if we're asked that are less than percent, so the probability that it's the lower end is going to be at the 99.7%. This would be the greater, but if we're stuck between two values, we use this one here. So we're looking for the exact middle, that 0.997 goes there. So like I said, just as a reminder, if you get that question, because I have something similar. But what we get here is a z-score of 2.968. So as a reminder here, we're talking about a distribution, and I'm saying that if 99.7 is here, then there's a z-score of 2.968 here. But that means there's a negative 2.968 here. So we have a z-score, and what we were asked to find here is we're asked to find the x value. So I've given you this formula before, but we know that if we have z-score and I want to solve for x, what we're going to have is that x is going to be equal to z times the standard deviation plus the mean. So my z-score would be, one would be a negative 2.968 times the standard deviation of 9 plus 42. So that would be my smallest widget. And then I would ask this again, running out of room here. Sorry, I'm getting messages from people. We could do that again here, except we're going to use the positive z-score over here. So then we'd also have one where we did 2.968, but I just wanted to remind us about this formula again, because we will see it in some capacity. No, it seems about right. For a second, I thought that was too big. Okay, so then one of the last things that we were asked a lot about was the stuff about groups. So like I said, a lot of it's going to go back to that stuff we did on z-score. So the population parameters are going to be your mean. So this is all population data, not sample. Is a mean of a 97.4 and a standard deviation of 79.3. And we're going to have a sample size of 142. So this goes back to that mean of the sample mean. So just as a reminder, if you need to find a mean of a sample mean or the standard deviation of a sample mean, the mean of your sample means is always your population mean. So in this case, it stays 87.4. The standard deviation of your distribution of sample means is population standard deviation divided by the square root of the sample size. So I do ask you this. So in this case, your standard deviation would end up being 6.6, we'll say 55. So we know that we do this when we have questions like we have down here. So a manufacturer knows that their items have a link that is right skewed, so it doesn't matter how things are the skew this time, with a population mean of 16.8 inches and a standard deviation of 4.6 inches. And what we want to know is that if 37 items are chosen, so we have a sample size. So this is one clue what we're doing. What is the probability that the mean length is greater than 15.5? Because we talk about a sample size and we want a mean. And a sample mean. is what we're given here. What we know that we're doing is that this is going to be data is going to require us to find the mu sub x bar and the sigma sub x bar. So this is when you do these kind of z-scores. You're trying to figure out where a mean is in relationship to other means. So this is going to be this equation here. So the sample mean, take away the mean of the sampling distribution divided by the standard deviation of the sampling distribution. Or alternatively, what we said we could write this, which we started doing towards the end of the class, is that the mean of the sampling distribution is equal to the population mean. And the standard deviation of the sampling distribution, it's just sigma divided by n, square root of n. Okay, so I use the stuff above as I needed here, so let me get rid of it for a second. So we want to know we have a mean of 15.5. We have a sample size of 4.6 inches. And I want a z-score for this data. So that z-score, like I said, is going to be x bar minus mu divided by sigma divided by the square root of n. So we have 15.5. The population standard deviation was 16.8, which is the standard deviation of sampling distribution. And the standard deviation of the sampling distribution is 4.6 divided by the square root. I wrote in the wrong sample size, sorry, 37. So this, I said, probably best you put the top and bottom parentheses when you put this in a calculator. So this ends up with a negative 1.72. So like I said, everything's here the same as finding z-scores and probabilities. Is just that you have to be in consideration of, are you doing this kind of z-score? Or are you doing one for a single value? But if we took that and we put it in our z-score calculator, so we want what's the probability the mean length is greater than 15.5? That wasn't my negative. So we're putting a 9.72 in here because that's a rounded version of that z-score. Make sure you don't have anything else filled in here. So the probability of being greater than is right here. So it would be your 0.957. So we were asked, what is the probability that I'd have a mean length greater than 15.5, which is the equivalent of asking for a z-score greater than negative 1.72. And we get 0. Let's say 975 or 957. Okay. So I don't think I rounded correctly, but that's fine. I was just trying to demonstrate quickly what you would do here. I'm trying to find where I am here. There's a question missing. Oh, right here. So 47, like I said, I just want to do that one first. This one is trying to find the minimum assembly time of the top 10%. So this is the same thing, is that we have time required to assemble a PlayStation is 15.03 minutes with a standard deviation of 1 minute. A sample of 16, we have a sample size. once I have a sample size, that's going to kind of tell me what I'm doing here of assembly times. We want to find the minimum assembly times for the upper 10% of average. Average means mean assembly times. So between having a sample and a mean, we know that we're looking for this kind of z-score. Got my bar a little too low. Okay. Or another way that we said this before, this is how we were doing it last time. So what we had said in the past was that what we're asked for is the average assembly times. I want that X bar. So just like the last time when we wanted just X, this means that it's going to be Z times the standard deviation plus the mean. So we want the upper 10% of assembly times. That means we have to use this one here for the upper tail. And we put in that 10%. And my z-score is 1.282. Like I said, if you're putting 10% up here, that's the z-score that goes with that. So if I just want to find that X bar, it's now 1.282. And then we need that standard deviation. So like we said, this standard deviation is sigma divided by square root of n. So we have a standard deviation of 1. We had a sample size of 16. And then our mean is just our normal population mean. So we're going to add that 15.03. So the minimum assembly time, so anything over 15.3503 has a 10% chance of happening. All right. So everything we did here led right into confidence intervals. All right. If I don't get through hypothesis testing, I'm going to record that into the next section. And like I said, I'm just going to, like I said, if you want to stick around, you can, but I'm going to post that all after I get the video done. So if you don't have anywhere to go, you can kind of stick behind, but I'll finish out that hypothesis testing if I can't get it done here. But like I said, next is your confidence intervals. So I do ask your confidence intervals similar to this at some point. I'm trying to remember if I asked you one or two. So I give you one confidence interval and I give you one hypothesis test. And one of them is going to have z-scores as your critical value. One's going to have t-scores as your critical value. So I'm going to do both versions for each of this. So if you are doing this one, the city wishes to estimate the average commute distance across a city. They collect a random sample of 53 people. And find that they have a mean, so it's a sample mean of 10. They also assume that the population standard deviation, so they give you sigma, is 1.7. So if they give you sigma, you're going to use z-scores. So we want to calculate the z-score to estimate the average. So we're using the z-score to find the confidence interval. Calculate the confidence interval. I reworded it so it doesn't look like it says it in here. But that's what that's asking you, is calculate the confidence interval of the mean for the average commuting time with a confidence level of 95%. So to do this, we need to find the z-score that goes along with this. So that's what this critical value is. So this critical value is that if 95% of my data is here, what's that z-score that binds it? So we go in here, and like I said, this one is the one we want to use for your confidence intervals, and we put our 95% here. So that's saying that's 95% that's bound between the z-scores. And that z-score is 1.96. And when we're doing confidence intervals, we only care about the positive z-score. So, confidence interval. Our confidence interval is going to be your point estimate. Which is always going to be your sample mean. So here we got 1.96. Point estimate's going to be 10. Your margin of error is going to be this z-star sigma divided by the square root of n. So all of this here is your margin of error. So what we have here is, if I'm doing this critical, not critical value. When I do this confidence interval, I have a sample mean of 10, plus or minus. Sorry, that was missing. The z-score, my critical value was 1.96. And then I had a sigma of 1.7, so I had a population standard deviation. And then my sample size was 53. So this part here, if I do that calculation, 1.96 times 1.7 divided by the square root of 53. I'm going to get 10 plus or minus 0. What am I rounding this to? Two places. So 0.76. 0.46, that is my confidence interval. Not confidence interval. That is my margin of error. I'm talking too long already today. So if I do 10 minus my 0.46, that's going to be 9.54. So that is the lower part of my confidence interval. If I do 10 plus my 0.46, that is going to be 10.46. That's the upper part of my confidence interval. So like I said, I do have it broke down like this. So you need a z-score or a t-score. Tell me the point estimate, your margin of error, and then your, like I said, give me the interval. So this one, I'm going to write it similar to how we did the last one here in a second. But a survey of 23 people, that's my sample size, on how much they spend on their child. The results were roughly bell-shaped. So this is telling me the results of the sample. So since it's results of the sample, this mean that I'm getting is a sample mean of 34 and a standard deviation, sample standard deviation of 9. We want to construct a confidence interval with 98% confidence. So we have a standard deviation, but it's not the population standard deviation. So we are going to use the t-scores. Let me bring up that t-score calculator here again really quick. I think I closed it down doing something. So we had 2 of them. So this is the first one. There we go. This is the first one that we had. So degrees of freedom, if you remember, that is sample size minus 1. And your significance level is 1 minus your confidence level. So this is going to be, we had a sample size of 23. So we're going to use 22 degrees of freedom. There you go. Trying to get that to go in there. And then my alpha here, that is going to be 1 minus, and we said my confidence level is 98%, so minus 0.98. So a 0.02. This is my alpha. We calculate, and as long as it's confidence intervals, we use the two-tail. So what we're getting here is I get a t-score of 2.51, is what we'll round it to. Okay. So the information we have here is that my critical value will be a t star this time, and that will be 2.51, I believe is what I said. Check that one more time. Yep, 51. My point estimate is still going to be the same. It's still that X bar. So it's going to be that $34. Your margin of error. So the one thing that is different here is when I calculate this confidence interval, I'm still using X bar plus or minus. What I'm using instead of a z-score is a t-score, and I'm using, instead of sigma, I'm using sample standard deviation S over the square root of the sample size. So this is my margin of error. So my margin of error is going to be, just a second, I lost my place here, 2.51 for the t-score. We had a standard deviation of 9 and a sample size of 23. My 23 looks like a 25, so I make that clear. That is a 3, but that margin of error is 4.71. So if I was to write my confidence interval in here, X bar, margin of error, we had a mean of $34 plus or minus $4.71. Okay. Like I said, the last couple questions, this might roll into the next section, so I'll just keep rolling into it. And if anybody is still around after this, I'll take questions. So one of the questions we had asked before, so this is one I didn't get to ask on a test, I don't believe. So which of the following would result in your narrowest confidence interval? So if you remember, we have larger sample size. Is going to lead to a smaller confidence interval or narrower. So if we get larger sample sizes, it narrows our confidence interval. If we use larger levels of confidence, this is going to widen my confidence interval. because it gives me a larger region to look at. So if I want to make the narrowest possible confidence interval, I'm going to need the largest sample size. So automatically these two are out. And then we know a larger confidence interval is going to make a wider interval. So I need a smaller confidence interval. So that should lead to my narrowest confidence interval. Like I said, if you just keep this with you, then it doesn't matter if I ask you for widest or narrowest, you'll be able to find it. Or if you do, like you run through these problems and it changes to a widest, you'll be able to do it as well. Okay. So your type 1 errors and your type 2 errors. I'm going to save this for last because this question is a little confusing. So what I'm going to start with is identifying. So you have a question like 24, sort of, except I kind of cut some of this out, this part here about writing the null hypothesis of words. I took this out because this is actually really confusing. I went through it again because and realized the wording is terrible. So I took out a question that was similar to that, but you are asked this. So suppose that BC Financial Aid allots a textbook stipend by claiming that the average textbook at the BC bookstore costs $88.87. This is a population mean. You want to test this claim. So if they're just saying that this is what's happening, you always ask, is my new mean going to be larger, smaller, or just different? According to this, so I'm just going to, like I said, rephrase this. This makes a little bit more sense for us. So if we were asked, is the average price cheaper? Then what we're asking for is the null hypothesis, no matter what, is always going to stay, yeah, book prices are 99.97. Or sorry, 88.87. I don't know what I'm seeing there. If the average price is cheaper, that means that we're looking at being down here. We're doing a left tail test. That would mean that the alternative hypothesis is that actually the mean of textbooks would be below the 88.87. If I ask you, is the average price actually higher? Like I said, this question was a little nebulous. It's actually asking you for a two-tail test. I made it a little clearer. If you're doing this, you're testing to see if you got a higher amount. This means that the alternative would be that the average prices are greater than 88.87. And what this is wondering is, are they just different? It doesn't specify that very well, but that's what it's basically asking. So if the average is just different, we don't know if it's higher or larger, that means that my null hypothesis is just whatever it is, the average cost of books is not 88.87. So I have one question where I give you a scenario and you just have to tell me which hypothesis test is it. And like I said, I'm going to do type 1 and type 2 errors last, because that's like worth 1 point. So if we are not great with that, we're fine. I am not going to do the confidence interval version of a hypothesis test. So as I said, I'm not going to do this hypothesis test in words because it's hard to word that in a way that makes sense sometimes. And I'm not going to do this one because this is the one that wants you to use a confidence interval. And I've already asked you to do confidence intervals. So I'm asking you to do, second, where'd those go? I think there's a problem. It's not showing up in here. This keeps doing it to me if I look at it in the wrong context. Just a second here. Give me the other view. Second, okay. I think that something glitched with my question there, so I have to go find it in a different place. So let me just do this instead. So like I said, I kind of asked you more like I did in your question, homework on these. I'll have to go figure out what happened. One class, actually, your whole review just disappeared and I had to add it back in again. Yeah, yours is missing a question in here. So let me pick a hypothesis test. So we did ones like this. So we know the average body temperature is 98.6 degrees Fahrenheit with a standard deviation of 0.72. So we've used this before. If I give you this information like that, I'm just putting a note here. There is no mention of sample size. So this is population data. So I know like the biggest part about this is going to trip people up is knowing whether you're using t-scores or z-scores. This is population data. So this is telling me that mu is 98.6 and sigma is going to be 0.72. Like I said, this is telling me this is population data. So since I have sigma, that means I'm going to use a t-score. So continue with the problem. So let's say there's a study states that women have a lower temperature. So our study here is we collect, let's say 100 women, just to make it easy. And those 100 women have a mean temperature of, let's say, 98.3. So all we're really asking here is, do I have evidence? Women have lower temperatures. So we already answered one question, do I use a z-score or a t-score? So what that means I have to find is, oops. So we have a significance level or alpha, so I'm going to use an alpha of 5% here, or 0.05. So we have two things that we really need to find here, actually three things, but we'll break it down to, we're using z-scores, so we need a test statistic. So this is going to be a test statistic of just your mean. So we had, this is a sample mean here. We're going to do a test statistic of that sample mean of 98.3, which means we're doing a z-score. So like I said, we're going to find two different z-scores. This is one of the things we're going to do. So we are going to have a 98.3 minus 98.6, because that was my sample or my population. And then we're going to divide by 0.72 divided by the square root. And we had a sample size here of 100. So that is your test statistic. So I'm going to find all this data, and then we're going to talk about how we do the test. But if we do this, oops, answer divided by 0.72 divided by the square root of 100. Actually, I didn't need to do that. It was a bunch of extra work. I get a z-score of 4.16. So then the other thing is we need that critical value. So to decide on what we're doing for a critical value is really looking at that hypothesis test. So hypothesis test, like I said, we expect that if nothing changed, women are still going to have a temperature around 98.6. If we are going with the data says we expect them to have lower temperatures. So we expect it to be something under 98.6. So we're doing a left tail test. And that alpha is down here. And we said that alpha was 5% or 0.05. So that tells me where I'm going to put it in here. So I want to make sure it goes, sorry, in that lower tail here. So I am going to put my 5% here to make sure it goes in the lower tail. We calculate, so my critical value for 5% in the left tail, like I said, depends on what tail we're looking at, is going to be a Z star, and that Z star is going to be a negative 1.645. So I'm going to erase some of the stuff at the top here in a second so we can keep going on with this. So like I said, I ask you first off when I give you a hypothesis test if it's a Z-score or a T-score. So if you mess up and you tell me it's Z-scores when it's T-scores or T-scores when it's Z-scores, I will follow the rest of the data. As long as the rest of everything else is correct, you'll get most of the credit for it. So don't worry that if you get that part wrong, the whole thing's gonna be wrong. So what we have is this information. We know that this is my distribution. Alpha here is 0.05, and the z-score that breaks that off is a negative 1.645. My test statistic, my z here, was a negative 4.16. It puts it in my critical region. So what we're going to do is, in that case, because we're in that critical region, that means we reject the null hypothesis. So another thing I'm going to ask you, in just a second, we just had somebody new join in. So just to let you know, if you got here, just got here and joined in, I'm continuing with what I left off with last time. So I'm just continuing with hypothesis testing, and then I'll start over and doing more of the review. I'm just trying to get one continuous part here. Okay, I saw that Jaden asked me for questions on the test. Do you mean this question I'm doing right now or a different question? Because I'm going to ask you one similar to this. Like I said, it's going to be a hypothesis test. I could do it a z-score and I could do it a t-score. There's only one slight difference, and it's just how you find the t-score, the test statistic. So the other thing we might ask for a p-value, and this will be a p-value for, once again, that sample mean. So if we do that p-value, the probability, in this case, because I'm in the left tail, my p-value is going to be the probability of getting means less than 98.3. So if you end up doing that, that's the same as saying, because we said the z-score for this is minus 4.16. So this one's x. Yeah, okay. Yeah, there's gonna be something very, at least if it's not exactly this question, it'll be very similar with a t-score instead. So like I said, somebody was asking me about that. So when you look for the p-value, you use your test statistic. And if I do that, what I'm seeing here is, like I said, I'm looking into that left tail being less than. I'm getting a probability of 0.00002. That is my p-value. And as long as my p is less than alpha, so because this is true, because my p-value was the 0.002, and we said that alpha is 0.05, p is less than alpha, we also reject the null hypothesis. So just as a little note here. Like I said, I'm just asking you if you reject the null hypothesis, but I'm going to ask you for the critical value, the test statistic, p-value, because I don't know which one you prefer, so I can just ask you all of them. And the one that makes the most sense for you, using the critical values or the p-value, use that one to determine if you reject the null hypothesis. So if we reject, that is a terrible color. We are going to reject the null hypothesis, which was stating that the means were the same. So if we reject this, we said we don't accept this. This means that we have evidence to support the alternative hypothesis, which is simply that the temperatures are going to be less than this. Sorry, body temps of women are lower. So if we reject the null hypothesis, then yeah, we have evidence of the alternative. Okay, so like I said, I'm going to do something similar again, but I'm going to do it with a test statistic so you can see, not test statistic, sorry, a test statistic of T, so you know kind of what the difference is that you're looking for. So like I said, you have one confidence interval and then one hypothesis. One uses Z-scores and one uses T-scores. That's why we're doing both of them right now. So we have two calculators that we need to use here for a hypothesis test. I'm trying to figure out the best place I can start writing stuff on here. I'm trying to move something out of the way here so I can do this. There you go. So the mean IQ of the population is 100. A sample of, let's say, 50 students taking fish oil, because fish oil is supposed to help. They had a mean IQ of 104 with a standard deviation we'll say 6. Let's do it 15. Let's say 10 because I'm trying to make it go a certain way. We'll see if we can get to do it. If I word it like this, we know that this is my sample data, or it's not my sample data. This is the only population data I have. This is all sample. So because I give you a sample size, I mentioned a sample size, and then I follow that with a mean. We know that this is a mean for a sample, and we know that this is a standard deviation for a sample. We have no sigma whatsoever. We were not given it. So we're going to use T-scores. So the question that ultimately we're going to ask here is there evidence?
Left.
If you got here a little late, and like once again, I'm saying I'm just finishing up what I was doing last time, and then I'll start over the rest.
Like 12 10. Like what the fuck? It is like, bro, my nigga, I literally just.
Okay, there we go. Is there evidence that fish oil is linked to increased IQ? So once again, we know that what we need is I'm going to use t-scores. Once again, what I need to find is I need a test statistic. And it's always for your sample mean, so a test statistic for that mean of 104. So this part's easy. We don't actually need a calculator for it because this is going to be your t-score, works like your z-score. So it's going to be t x bar minus mu, except we divide by the sample standard deviation divided by the square root of the sample size. So I forgot that I had here. I'm going to use an alpha of, let's just do 7. We did 5 before. I'll do 1. Let's use 1. So when I do my critical value, this is a critical value for an alpha of 1%. So like I said, test statistic is always on that sample mean. Critical value is to deal with your alpha. So here, if we want to do the critical value, we would use this particular calculator. So I'm going to do the test statistic after I do this. But as a reminder, this is the situation. Null hypothesis is that these people in fish oil still have the same IQ. Alternative hypothesis is that we want evidence of an increase in IQ. That means IQs are over 100. So what we're looking at here is that my alpha has to be up here, and I want the t-score that tells me where that is. So once again, my degrees of freedom. So I want to fill this out. Sample size -1. I had a sample size of 50. Right here, I mentioned it. So my degrees of freedom are 49. This is why you only have one hypothesis test on your test. We said that alpha was going to be 1%. And we hit calculate. So this time, remember, we're not doing confidence intervals, we're doing tests. So just to put on here again, if you end up having a left-tailed test, right tail is going to be, this score is going to be 2.40. We'll leave that at 2.40. If it happened to be a left tail test, we would say T was a negative 2.40. So it's just like we did with z-scores. Okay, so if we just want your test statistic and your critical value, we just need this calculator. All right, so doing your test statistic now. So like I said, I just need right here, the sample mean. So we had a sample mean of 104. We know population mean is 100. And then we're just using the sample standard deviation of 10 divided by the square root of my sample size of 50. So if we do this, we get 104 divided by, so second, 10 divided by the square root of 50. So I'd say remember putting parentheses here just to make sure. But your test statistic is 2.83. Dang, I should have made this a harder test. I mean, my alpha level. Okay. So I'm going to get rid of this information over here for right now. So once again, we're in this situation. So this is going to be another one where we're going to reject. So if I have my alpha is just going to be this 1% in the tail, my test statistic here is going to be 2.4, not my test statistic, sorry. My critical value is here. My test statistic it's not the T star, this is just the T. This is 2.83. So according to this, once again, this score, if I look at this as a number line, like this is 0 here, this score ends up in the critical region. So we reject the null hypothesis. We have evidence of the alternative hypothesis, which is IQs are going up. We have evidence that fish oil is linked to increased IQ. All right, and now I'm going to do this with the p-value here in a minute. So p-value will still come out to the same decision. It's just how we calculate the p-value. I just want to make sure you have that. So we had this other calculator right here. And what we want is the p-value for the sample.
Is the calculators going to be linked to the test tomorrow?
Yes, I have them all linked in there.
Yeah.
P-value for X bar was 104. Okay, trying to remember what it was. Yeah, so a question like this will be on the test. Somebody just asked me that. All right. I forgot what my number here was. So if you remember, what we had here is we had a T-score. The T-score for an X bar of 104 we said was going to be 2.282, sorry, 83, 2.83. I believe is what we said. So we're using basically that test statistic. So when we do this, we want to make sure that that test statistic, that T-score goes in here. We also need the degrees of freedom. So we already figured out degrees of freedom with sample size -1. We had a sample size 50 -1. My degrees of freedom were 49. And we are doing a one-tail test. The rest of this, if you don't get this filled in right, that is fine. Because what I'm asking you for is the p-value. So I would say that the p-value is this. P is 0.00337. And what we know p-value is telling me is the same thing as any other probability. P-value is the probability that I had a sample mean, because my hypothesis test said we were looking at means over 100. So we're looking for means over 104. Like I said, we're just matching the tail. So we're matching that right tail. This is the equivalent of saying that my T-score is greater than 2.83. If that is true, that probability is 0.00337. So what we said is that my alpha level this time was 0.01. So if my p-value once again is less than alpha, so p is less than alpha, once again, we reject the null hypothesis. Right. And I'm gonna go fix your review to make sure, try to find a question like this that fell out of it. So the last things, and like I said, depending if you're which section of the class you're in, you may have some of these problems. We will have this one. So I just wanted to reword this. So what I wanted to say here is a type 1 error. This is where you initially are going to reject your null hypothesis. But null was true. So this is a case where you reject the null hypothesis and then saying that something made a difference, but it doesn't. So usually a key here is just looking for, did I reject the null hypothesis and then things change later. Type 1, this is where we fail to reject the null hypothesis. It turns out the alternative hypothesis was true. So this one's weirded little word. It's got a weird wording, so I changed the wording on your exam so it makes a lot more sense. But a manufacturer's cell phone battery markets its batteries as having, on average, 500 charges. A consumer group decided to test this claim, assessing 30 of their phones. You don't actually need this information here because they tell you your p-value is 0.111. And I always say, assume alpha is going to be 5% unless you're told otherwise. So we're assuming this is what that is. So your p-value is not less than alpha. So we fail to reject. We only reject a null hypothesis if we're have a less than 5% chance of happening. The resulting p-value was 0.111, thus the null hypothesis is not rejected. So this is later. Later, the consumer group decides that the manufacturer's claim that the cell phone battery can be recharged on average 500 times is accurate. So what this is saying is we failed to reject the null hypothesis, which means that we rejected the alternative. This is a weird wording, but like I said, what you're looking for is when you're asked for a type 1 or type 2 error, did we reject the null hypothesis or fail to reject it? So if you're trying to quickly figure it out, if you failed to reject it and you shouldn't have, then that's your type 1 error. In this case, we shouldn't have because when we rejected it, we said that, no, this wasn't what was going on with the batteries. Well, like I said, I worded it a little clearer, so it's a little easier to read than this, but that's typically what we're looking for is, did I reject the null hypothesis or did I fail to? Because in the end, what happened is whatever you picked was ultimately wrong in the end. And you just need to figure out this first part. Like I said, this is 1 point on 42 questions. If you miss this one, you're going to be okay. Okay, so we asked that one. Okay, so as far as everything else we have, so like I said, depending which class you are, this is going to be different. If you are in the Monday, Wednesday class, I'm going to ask you to look for look at correlation coefficients and match them. I'm asking you that for both classes. Where the difference is that if you are in Monday, Wednesday, I'm asking you to describe slope and intercept for a linear equation and to find me a linear regression. If you are in the Tuesday, Thursday class, because we didn't get to cover that last part well, I'm asking you to find a correlation coefficient. Did I ask you for coefficient combination? What was the I think it's correlation coefficient and check the relationship. So I'm going to go through this and make sure I cover all that. So some of this is going to be different depending on your class. But first things first, is this a linear or non-linear scatter plot? So remember, linear makes a straight line. This doesn't make a straight line. This makes a curved line, so it is nonlinear. So that was like one question there. Trying to get to move the other ones. Like I said, I'm going to ask you one like this. Of course, it doesn't fit in here super great. But just sort of make it clearer than these ones. Each scatter plot shown with one of 4 of the correlation coefficients. So as we see, this data has a kind of negative trend to it. So it's going to be one of these negatives here. So this one's probably, I'd say, the D, because it's has a negative trend, but very spread out. So that would be my guess on this one. Like I said, as far as your test goes, because I didn't use Lumen for your tests, thank goodness, your stuff is much clearer. Yeah, that would be that one. This one, as you see, is generally, like if you're trying to close off the area, this is a sort of vague positive trend. But we don't have, it's very spread out again. So you would have a positive correlation coefficient, but you're going to pick one closer to 1. So this one would probably be A. So the other ones we have, I'm going to write them down here because I'm going to move the screen down. We're going to miss them. So what we have left is B, which is 0.88. And we have Z, which is negative 0.72. So these ones are going to be much clearer. Oops. And then I erase everything I write. So if we look at the last two, as we see, is things are a little more clustered together in a negative trend. So because it's negative and the number is a little bit closer to 1, we'd end up picking C. So like I said, the closer it is to 0, the more spread out it is. The closer that value is to 1 or negative 1, the more your data is clustered together in a line. So this one here, like I said, data is very much clustered and it's all going in a positive direction. So this one would be your B. So this question usually goes off without a hit. I'm trying to find that extra problem I threw in here. So as I said, if you are right here, So like I said, Monday, Wednesday class, you might see a problem like this. A researcher wishes to examine the relationship between years of schooling completed and the number of pregnancies in young women. Her research discovered a linear relationship and the least squares line is y equals 3 minus 1x. And we know x is representing the number of years of schools complete of schooling. And y is representing number of pregnancies. So we want to interpret the slope of the regression line. So as a reminder, this is slope. So what slope is always your y over your x. So it's going to be number of pregnancies for years of school. So if it happens to be -1 as my slope, what that means is that that -1 is basically going to the top. So you're saying you have -1 pregnancies for years of school. So first one here, amount of schooling increases by 1 year, number of pregnancies decrease by 3. No, because they're talking about intercept. Numbers of years of schooling increased by 1, number of pregnancies increased by 3. No, still talking about intercept there. These two, they mention your slope. Year of schooling increases by 1, number of pregnancies increase. Well, we had a negative slope, so this one's wrong. So you're looking at this one here. The amount of schooling increases by 1 year, the number of pregnancies decrease by 1. So for each year of schooling, the average number of pregnancies decrease by 1. All right, and then a question like this one. One of the nice things is you're able to copy and paste. So I just take that and then just copy all of it. The data below has been collected on different fields of various, collected from different fields from various farms in certain valleys. The table contains the grams of raspberries tested and the amount of vitamin C in milligrams. We want to do a linear model to see if basically, if we have more grams of raspberries, is there more vitamin C? That's essentially what we're looking at. Okay. If I try to go through it straight way, it cuts me off for some reason. I tested your link. Your link goes right where it's supposed to. It's just when I try to do it on here. So we want a linear regression. So I copied that data. I can just paste it and hit submit. But it shows me the data and it gives me the equation for the line. So it's showing me here that my equation for the line would be y hat is equal to 0.44, I'm going to round it to 29. And you see the x is on that first number, so I put the x there, minus 12.3714. So 3 decimal places. So we said that you see it's putting the x here, so we just make sure the one with the x on it sticks together. And this is the number without the x, so it goes here. So make sure you put in the negative because it was a minus 12. So if we tested 140 grams of raspberries, what is expected vitamin C content? rounded to the nearest tenth. So as a reminder, you just go back here. We put in 140. And we get y is 49.6. All right. So if you were, like I said, Tuesday, Thursday, what you would have done instead is you would taken that same data, except that instead of doing the regression line, I just ask you to do a correlation coefficient. So in that case, if you're in that class, your correlation coefficient, you can just say R is 0.9996. We'll round it there. Whatever I picked, I made sure that it was something that was easier to round. But I just wanted to double check that I have this. Okay. Zoom recording. Okay. So we just have this on the video here. Like I said, this is the breakdown of what you're looking for, which problems, if you want to study it. Hypothesis testing, I'm going to, like I said, I'm going to go back and see if I'm just getting a different version of the test when I'm looking at it. But I might go back in and add some questions just so you can do that hypothesis testing again, because I'm not sure why they're missing. And then, like I said, just a note, you're not going to do tons of T-score problems. You're going to have like one problem, I believe, with a T-score. Okay, so like I said, there's 15 minutes left here if you guys have a question. If you don't, I can stop here and then I'll get the recording up as soon as I can, which would probably be like maybe an hour at most. The longest part is just going to get the whole thing to download off of Zoom. And once I got that, the rest of it's going to go quick.
Okay, can you do a quick breakthrough? Can you hear me?
Sorry, what was that?
Can you do a quick breakthrough of what the X with the line on top, what that means and stuff like that?
The X with the, okay. You mean all the symbols?
Yes, please.
Okay.
I'm sorry.
That's okay. So if you have sample data, we use N for sample size. We use an X bar for a sample mean. We use S for a sample standard deviation. Is this sharing?
Yes.
Okay, just make sure it was. Sometimes it doesn't do it. If we're dealing with a population, then we're not going to worry about this. We're not going to have sample sizes for that. You are just going to have mu, which is population mean. And then we have sigma, which is going to be population standard deviation. Then we had your distribution. Of sample means. So this is me, we were comparing everything to a mean. So everything was like looking at an X bar here. So in this case, we had mu, and it was a subscript X bar, and mu subscript X bar was your mean of sample means. So the mean of all your sample means.
And that's always going to equal the mean, right?
What was that?
It's always going to equal X, right?
Or yeah, the population mean. And sigma sub X bar is your standard deviation of your sample means. And the formula for this was population standard deviation divided by the square root of the sample size. So we had, if we were talking about a single value X, if we were doing z-scores, it was X minus mu divided by sigma. If we were looking at a mean of a sample and we did a z-score, so the mean of samples X bar, this will be X bar, and we have to compare it to the mean of all your means and the standard deviation of all your means. So we can write it like this. But we know that the mean of your means is population mean, and the standard deviation of your means is just population standard deviation divided by the square root of n. I'm trying to think if I'm missing a formula here. Confidence intervals are the only other ones I'm missing, I think. So the other formulas we have, if you have to find a t-test statistic, that was going to be very similar to what we do with the x's here. So we do x minus mu, but we divide by the sample standard deviation divided by the sample size. And then if we're doing confidence intervals, if your sigma is known, then we do, your confidence interval is going to be X bar plus or minus your critical value Z divided by sigma divided by the square root of n. If it's unknown, then we use t-scores. So instead we use t, the critical value of t, and then we use s because we don't have sigma divided by the square root of n.